I had a bit of a crisis the other day. I was typing this fairly important email on my phone. Thumbs flying, not really looking, and I hit send.
Oh, no.
I looked back at the sent message, and autocorrect had changed securing the contract to recurring the contact.
Ouch. That changes the tone of the negotiation quite a bit.
Just a little. But, after the panic subsided, I found myself just staring at that little glass rectangle and wondering, how does this thing actually work?
Right.
We spend half our lives typing into these devices, using spell checkers, using Google Translate. But have you ever really stopped to think about how a computer actually understands what a word is?
It's the invisible infrastructure of our daily lives, isn't it? We just take it for granted, but under the hood, the complexity is, well, it's staggering.
Right. Because to me, words are obvious. Run, running, ran. They're all just flavors of the same idea.
Mm-hmm.
But to a computer, run and ran are totally different strings of data. Ran actually looks more like fan or pan than it does run.
And that's the fundamental disconnect. To a human, language is intuitive, it's all linked by meaning. To a computer, it's just a string of ASCII characters.
Just ones and zeros.
There's no inherent meaning there at all, just patterns.
And that is exactly what we are unpacking today. We're doing a deep dive into a field called computational morphology. We've got a whole stack of research here, drawing heavily from the work of Kemal Oflaser and other pioneers to figure out the algorithms that slice and dice our language.
Our mission really is to look at how we teach computers to take those raw strings of characters and map them to actual human meaning.
Yeah.
And we should probably warn you, while English has its quirks, there are languages out there that are absolute nightmares for a computer to process.
I saw some of the examples in the research notes. I mean, languages where a single word is basically an entire sentence.
Oh, it gets wild. And the big takeaway here isn't just about grammar rules. It's about how we bridge that gap between human logic, which is messy and historical.
And evolving.
And evolving, yes, and computer logic, which demands absolute binary precision.
So let's start at the absolute bottom, the foundation. The research keeps coming back to this concept of the morpheme. Now, I remember this term vaguely from high school English, but what are we dealing with here?
Think of morphology as the structural engineering of words. If a sentence is a building, the morpheme is the brick.
The brick.
It's the smallest unit of linguistic information that exists.
So is a morpheme just a fancy word for word?
Sometimes, but not always. We have two main categories. First, you have free morphemes. These are the words that can stand on their own 2 feet. Cat, blue, walk.
Okay, that's straightforward enough.
They don't need any help. But then you have the bound morphemes. These are the hangers-on. They have to attach to a host to have any meaning.
Ah.
Think of the S at the end of cats. You can't just walk into a room and say S and expect people to understand you.
They'd think I was hissing at them?
Exactly. But when you attach that S to cat, it uploads a very specific piece of data, plurality. Or think of in unhappy. You can't use as a standalone word, but it carries the data of negation.
So cat is the hardware, and S is like a software patch that changes the specs.
That's a great analogy. Now, where this gets fascinating for computer scientists and frustrating for programmers is that not all languages handle these Lego bricks the same way.
This was the part that really surprised me. I just assumed all languages were built basically the same way,
Not at all.
A subject, a verb, maybe some endings.
Yeah.
But the architecture is totally different depending on where you are.
It's a whole spectrum. On one end, you have what we call isolating languages. Mandarin Chinese is the classic example here. In an isolating language, those bound morphemes, the parasites as you could call them, are very rare.
So I eat apple is just 3 distinct blocks. No changing eat to ate or eaten.
Generally, yeah. The context tells you the tense, not a suffix. For a computer, this is actually a bit easier, morphologically speaking.
But then you swing to the other extreme, which the notes call agglutinative languages.
The beads on a string model.
Right. And Turkish is the poster child for this. This is where my brain started to hurt.
It's a lot to take in.
In these languages, you take a root word, and you just keep gluing morphemes onto it, one after another after another.
And the key feature of agglutinative languages is that the seams are visible. You can see exactly where one bead ends and the next begins. Each bead carries exactly one piece of information.
Okay, I have an example here from the text that, honestly, I'm going to apologize to any Turkish speakers listening, but I have to try this. The word is gid ibolasektim.
Not bad. You got the rhythm. And that is written as one single word in Turkish.
One word. But the translation in our notes is a full English sentence. I would have been able to go.
That's it. Now, let's reverse engineer that because this shows the computer's challenge. You start with the root gid, that means go.
Okay, go.
Then you glue on able, that bead adds the concept of ability or can.
So goable.
Then a sick, that sets the future tense. Then tie, that adds the past tense.
Wait, future and past in the same word?
Would have been. It's a future possibility looked at from the perspective of the past. And finally, arma, which flags it as first person singular. I.
That is just incredible efficiency.
Yeah.
You're packing 5 distinct concepts into one string, but it sounds like a nightmare for a dictionary.
It's impossible for a standard dictionary. In English, a spell checker might have a list of valid words. Walk, walks, walking, walked.
Right.
In Turkish, because you can stack these beads in so many combinations, the number of potential valid words is, well, mathematically infinite.
So if you're programming a spell checker for Turkish, you can't just look up the word in a database.
You'd run out of memory before you finish the A's. You need an algorithm that acts like a precise buzzsaw. It has to catch that long string and slice it up. Chop, chop, chop.
And that's distinct from the next category, inflectional languages. Spanish is listed here. How is that different from the Turkish bead?
It's messier. In Turkish, one bead equals one piece of info. In inflectional languages like Spanish, the beads melt together. Take the Spanish word hablamos, we speak.
Okay, hablar is to speak.
Right. The ending mos isn't just doing one thing. It's telling you we, it's telling you plural, and it's telling you the tense. It's a fused package. You can't slice it apart into person bead and tense bead.
So the computer just have to recognize the whole package as one thing.
Exactly. And just to complete the tour of horrors for the programmer, you have polysynthetic languages, like some Inuit languages. Here, the morphology is so aggressive that the word starts eating other parts of the sentence. The verb can swallow its own object.
So I eat the apple becomes one giant word sentence hybrid like I apple eat.
Essentially, yes, the boundaries of what constitutes a word versus a sentence become very, very fluid.
It forces us to realize that our Western definition of a word is just a convention, isn't it? Not a universal law.
Precisely. We think spaces define words, but that's just a typing rule.
Now, there's one more way to build words that I found really interesting because it feels like code encryption. The notes call it non-concatenative morphology.
Yes, the Semitic languages, Arabic, Hebrew. This is where things get really abstract.
This isn't just gluing things to the end or the beginning, right?
No, think of this as a root and pattern system. In Arabic, the root is usually a sequence of 3 consonants. For example, KTB.
Okay, KTB. And that implies writing.
KTB is the abstract skeleton of writing, but you can't pronounce KTB. To make a word, you have to apply a template, a pattern. You slot vowels in between those consonants.
Like filling in the blanks.
Exactly. If you use one vowel pattern, you get kitab, which means book. If you use another pattern, you get katib, which means writer.
Wow.
Use a more complex pattern, you get katab, to cause to write.
That's wild. So the consonants are like the variables in an algebra equation, and the vowels are the function you run them through.
It's incredibly mathematical. For a computer to understand Arabic, it can't just look at the edges of the word. It has to X-ray the word to find that consonantal skeleton inside.
So we've got beads on a string, fused endings, and X-ray skeletons. But here's the rub, and the Nopes call this the ambiguity problem. Just because we know how words are built doesn't mean the computer knows which blueprint was used.
Ambiguity is the arch enemy of automation. Humans are great at context, we use it subconsciously. Computers are terrible at it.
The example that really stuck with me was the English word second, S-E-C-O-N-D. I look at that, I see one simple word.
A computer looks at that and sees a logic bomb. Morphologically, second has at least 6 different interpretations.
6. I can think of time and like coming in second place.
That's the noun for time and the ordinal number for position. But then you hit the verbs. You can second a motion in a meeting.
Oh, right. I second that.
That's an untensed verb. But you can also say, we second this motion. That's present tense.
Okay.
Or you can yell, second this motion. That's an imperative command. Or, I requested that he second the motion, subjunctive.
And to a computer program, those are all distinct tags.
Yes. To a parser, second plus verb plus press is a totally different object than second plus verb plus imp. And the computer has to guess which one you meant.
And that's just English, which is supposed to be relatively simple. There was a Turkish example in the notes, okuma, that sounded genuinely dangerous if you got it wrong.
Oh, okuma is a classic trap. To the eye, it's one string of letters. But depending on how you slice the morphemes, it means 3 completely unrelated things.
Okay.
One, It's the infinitive verb reading.
Writing. Got it.
Meaning 2, it's a negative command. Don't read.
That's a pretty big difference. Reading is fundamental versus don't read.
And meaning 3, it's a noun phrase. Oko means arrow, is the possessive my. A is the dator case 2.
To my arrow.
To my arrow.
So a computer scanning document has to decide, is this text about literacy, government censorship, or archery?
Precisely. And that brings us to the engine room. How do we actually solve this? The technology that makes this all possible is called finite-state morphology.
Finite-state transducers.
Yeah.
It sounds like something from a sci-fi warp drive. How do we visualize this?
Imagine a machine with 2 conveyor belts running through it. We call them tapes.
2 tapes.
The upper tape is the lexical side, the abstract meaning. So it has a tag that says happy plus adjective plus superlative. That's the code.
Okay. That's the computer's internal thought.
The lower tape is the surface side, the actual spelling humans see, HAPPIEST. The finite-state transducer, or FST, is the gearbox connecting them.
So it's two-way translator. Logic to text and text to logic.
Exactly. And it has to enforce 2 sets of laws. First, morphotactics. This is the traffic cog. It decides which morphemes are allowed to touch each other.
Like knowing you can't put a past tense ending on a noun. You can't table something.
Right. The morphotactics would just block that path. But the coolest example of this is something called zero morphology.
The sheep example. I loved this.
It's so elegant. So usually in English, plural equals add an S, cat, cats.
Right.
But sheep is just sheep. 1 sheep, 2 sheep. So the FST has a rule. If the input on the upper tape is sheep plus plural, the output on the lower tape is sheep.
It translates the concept of plural into nothing.
Into a 0, an empty string. The computer knows the plural tag is there on the upper tape. It's just programmed to realize it as invisibility on the lower tape.
That is deeply cool. It's like a phantom limb. It's there, but you can't see it.
Then you have the second set of laws, morphographumics. That's a mouthful, but it just handles spelling changes when morphemes crash into each other.
Like when the Y turns into an I in happiest.
Yes. Or gemination, doubling a letter. Stop plus ing becomes stopping with 2 P's. The transducer has to handle that rewrite on the fly.
The Turkish example for this was vowel harmony, which sounded like a very strict nightclub policy.
It is. Turkish vowels are very cliquey. If the root word has a back vowel, like a, the suffixes must also have back vowels.
So they have to match the vibe of the root.
Oda, room, becomes odalar. A matches A, but Ev's house becomes Evler. The E forces the suffix to change to an E sound. It's a chain reaction. The FST has to enforce this ripple effect.
So we understand the machine, but someone has to build this machine. The notes describe 2 main ways programmers historically wrote these rules: 2-level morphology and cascaded rules.
This is really the difference between a parallel processor and an assembly line.
Break that down for me.
2-level morphology is the classic, rigorous approach. It uses feasible pairs. It looks at the upper lexical tape and the lower surface tape simultaneously.
Just checking everything at once.
It's a set of constraints. It says you can have a lexical U paired with the surface eyes, but only if it's followed by an E. It scans the whole environment at the same time.
That feels very rigid.
It is. It's logical perfection, but it is incredibly hard to write. Cascaded rules, on the other hand, are more like a waterfall.
Hence the name.
You have a series of rules, step by step. Rule 1, delete the final vowel. Rule 2, apply vowel harmony. The word passes through one gate, gets changed, and moves to the next.
Since I have that Turkish word ata plus ior.
Step 1, the rule says delete stem vowel A before I. Now you have at. Step 2, attach the suffix, result, atior.
That seems much easier for a human to design. You can troubleshoot it step by step.
It is. But, and here's the giant pivot in the field, both of these methods have a fatal flaw.
Which is?
They require a human linguist to sit down and write thousands, sometimes tens of thousands, of rules by hand.
It's manual labor, and humans make mistakes.
It's slow, it's expensive, and for some languages, it's never-ending. That's why the field is moving so aggressively toward machine learning.
We're moving from rule-based to data-driven. Instead of teaching the computer the rules of English, we feed it 1 billion words of English text and say, you figure it out.
Exactly. The notes mention unsupervised learning. Systems like Linguistica or Morphessor.
How does a computer learn grammar without a teacher?
Statistical probability. It's actually quite brilliant. The computer scans 1 million words. It notices that the string, ing, appears at the end of thousands of different words.
Walking, talking, eating.
Singing, right. So it deduces, hey, this chunk seems to be detachable. It cuts it off and says, this is a statistically significant segment. I'll call it a suffix.
But does it know what ing means?
No, that's the catch. It knows ing is a structural piece, but it doesn't know it's a gerund or a participle. It's flying blind on meaning, but it's incredibly accurate on structure.
And that leads us to the absolute cutting edge, deep learning, neural networks.
The term here is morphological reinflection. This is where we use recurrent neural networks, or RNNs. We don't even tell them about suffixes anymore. We just train a massive brain. We say, here's jump, here's jumped, here's walk, here's walked. Now here is text. What is the past tense?
And the neural net calculates the probability and spits out texted.
Based on the vector patterns of millions of other words, yes. And it is incredibly accurate. It is currently the top performing approach.
But it's a black box, isn't it?
Yeah.
We don't really know how it decided texted was right.
We don't. We lost the rule book. We just have a math equation that works.
That's a little unsettling, isn't it? We started this with these elegant beads on a string, understanding every seam, every rule, and now we're relying on a neural network's best guess.
It is. It changes the role of the computational linguist. We used to be architects designing the building. Now we're more like trainers, trying to get a beast to perform a trick.
So bringing this back to the listener who is just trying to send a text message without looking foolish, why does this all matter?
It matters because language is the interface for everything now. Every time you speak to Siri, every time Google translates a web page from Turkish to English, these algorithms are running. They are stripping off these beads, finding the root, and reconstructing the meaning in milliseconds.
It's the universal translator, built one morpheme at a time.
But I want to leave you with a thought that kind of keeps me up at night.
Lay it on me.
We've moved to a world where computers learn language by looking for statistical efficiency. They don't know history. They don't know why sheep is plural. They don't know the etymology of night having a silent K.
They just know the math.
They know the pattern, not the story. So as these systems generate more and more of our text writing, our emails, generating articles, what happens if the computer decides that a certain rule is inefficient?
You mean, what if it starts generating patterns that work mathematically, but cut ties with the history of the language?
What if the machine starts streamlining our language for us? Like, why have fuf in phone when F is statistically more probable?
Exactly. Are we teaching them our language, or are they slowly going to teach us theirs?
A secret language of efficiency hidden inside our own.
That is definitely something to think about the next time you blindly accept an autocorrect suggestion.
Don't just click accept.
Never just click accept. Thanks for joining us on this deep dive into the machinery of words.
Pleasure to be here.
We'll see you next time.